before we start, I've been having all the courses videoed, but the person who volunteered to actually put them on the internet has been utterly unreliable. Utterly unreliable. I think there are only 3 or 4 of them, of the classes that have actually been posted. So there are 2 issues. One question is there someone who will actually do it? And then is there someone who can deal with a YouTube channel and uploading stuff? It's for the benefit of your classmates. Are you listening or are you just looking at your phone? Okay. So no one wants to do it. Okay, I'm trying to help you by videoing. If no one wants to actually take the trouble of putting it on the internet.
I can give it a try.
Huh?
I can give it a try.
Okay. Otherwise, there are videos of last year's class, which is almost the same thing, which I think you have the
links.
The link to. So if you send them to me again, I'll post them.
Okay.
So that people can look at last year's classes, which are similar. Obviously, it's the same material, but you explain things differently every time. So at least you'll have access to that. Okay. So, again, before we started this class, all your other classes were in the land of steady state, in steady state land. In this class, we're dealing with unsteady state land because the whole issue of control is to make sure that our system either reaches the steady state of, or desired steady state, or stays there once we get there, because there are constantly disturbances that will try to, there are natural disturbances that are constantly occurring that could try to kick our system away from the steady state that we calculated in all our other classes. Now, that was the introduction that we started with in the first class at the end of August. 2 months ago. Now we're really mid-semester, and you might have noticed that what we've done till now is we haven't done any control. What we've done is we've looked at systems and seen how can we model them in an unsteady manner, which is something that you never really did seriously in any other class. And not only how do you model them in an unsteady manner, but how do you analyze those models? How do you look what happens as a function of time? So, the first question we ask is, how do we know that the system is stable? Will a small perturbation grow, or will it shrink and take me back to the steady state that I started with, if I started with the steady state? If I do if there's a step change to one of the inputs, will the system go crazy, or will it settle down to a new steady state? Those are questions we ask without any control. That's the system responding to the environment, and we're just the observer. So we looked at what happens if there's a pulse change to one of the inputs. What happens if there's a step change to one of the inputs? What happens if one of the inputs has periodic behavior, for example, sinusoidal behavior? What will the output look like? Again, we haven't done any control. These are the system's responses to the environment or to whatever the inputs are. At this point, now that we know how to analyze the system, how to analyze it with respect to, in an unsteady manner, with respect to environmental disturbances or changes in the plant, etc., now we can say, well, if we know how to figure out how the system responds to changes we have nothing to do with, then we know how the system would respond, or how to analyze the system's response to changes that we do. In other words, let's say we know that there are going to be disturbances from the plant, from the environment, that are going to try to perturb the system and push it away from the behavior that we like. Maybe we can try to figure out how we can counter those effects with disturbances that we intentionally input in order to get the system to do what we want. And that's known as control. But all the mechanisms that we've used until now, the analytical mechanisms, to actually analyze the response of the system to disturbances, will also work for the response of the system to our control. And And the question we want to ask now is, if the disturbances are going to cause the system to do something we don't like, can we input our own disturbance, which we're going to call a control action, to make it, to counter the effects of the external disturbances, so that the sum effect of all will give us what we like. So that's the idea. Can we find a response that will make the system do what we want despite the external disturbances? And that's the question of control. That's what we're trying to do. So now, with feedback control, as we said in the first class, we may have a process with inputs, and those inputs may or may not be disturbed, and then there's an output. But now what we want to do is we want to measure that output, have some sort of controller, and affect the inputs so that the final output will be what we like. So that's the idea. We want to add this control loop, and we'll be much more specific about that control loop over the course of the hour. So before we can actually talk about those, now by the way, you can notice that without this, it looks kind of like a linear system. Once I put this in, you see there's feedback here. So let's call this FB, controller feedback. In the terminology of control, this is called open loop because there's no loop. And this is called closed loop because you see you have a loop. So it's open versus closed loop. And very often when you deal with control systems, you may want to look at the open loop process, that is just the natural disturbances. And then what happens when you put the controller? No, this is just the terminology that we use, open loop versus closed loop. Okay, well, in order to do that, we have to, first, before we design a controller, which is our goal in the next few classes, before we design a controller, we need to identify certain variables. First, there's the control variables. There are the control variables, there are disturbance variables, and there are manipulated variables. The control variables are the ones we want to control. Those are the ones we care about. So for example, the output concentration, the temperature, etc., the height in the tank, L. Those are things that we want to make sure that they're according to spec. The pressure, for example. We want to make sure the system doesn't blow up. A certain height, we want to make sure that the system doesn't go dry and that it doesn't overflow. The temperature, again, we don't want it to be too hot because it could destroy the sensors, etc. Disturbance variables, things that get disturbed. Well, what we've seen so far is we can have flow rates that are disturbed. We could also have input temperatures that are disturbed. We can also have input concentrations that are disturbed. So these are things that are disturbed without us doing anything for them. And the manipulated variables, we can manipulate volumetric flow rates. And typically, our manipulations are done with valves. We could, typically we manipulate volumetric flow rates, and we do that via valves. There could be other manipulated variables, but let's try to keep the list short for the moment. So the idea is there are disturbances to these variables, which we can't control. They affect the variables that we want to control, and we usually have some valves that control flow rates that we manipulate in order to counteract the disturbances on these so that we get the right answer here. That's the basic idea. Now, did I leave anything out there? And the trick for doing this is how do you do that? do this with a control algorithm, which we will talk about probably in the next class. I doubt if I'll get to that today, exactly what a control algorithm is. A control algorithm basically says, when I measure these and they're not what I expect, what do I do with these in order to get it to work? So that's what we're going to talk about, probably next class. Now, as I said, typically the way the control variable, the manipulated variables that we manipulate, the easiest way to manipulate them is by valves. If we have a flow rate and we want to increase the flow rate, well, we open the valve. If we want to decrease the flow rate, we close the valve. That's pretty easy. Now, of course, how do you close a valve? You could have a little motor there that closes the valve or opens the valve. Usually you don't want to do it that way because the motor has a power supply. And if you're dealing, say, with some petrochemical, for example, there could be a spark and it can explode. So you really don't want to do it with the motor. What you want to do it is with compressed air. If you do it with compressed air, then typically, so if you have a valve, then the valve could be quite a ways from your process. It could be hundreds of meters away. Or if you want, and you could have compressed air that's opening and closing that valve. So we typically try to work with compressed air. Now, and we'll again talk a little bit more about that as we go along. Now, first let's talk a little, before we go on, let's talk a little bit about time scales. There's a little picture here which I copied out of the book, which has a processor. And let's look at what's going on. There's a process which is doing something. So it could be a chemical plant, for example, making a component for your smart television, for example, by Samsung. Or it could be making some sort of chemicals. Now, if I'm interested in the temperature, if I want to make sure that the temperature doesn't go too high, then I have to measure the temperature with a thermocouple that's usually not directly in the process, but in some thermal well. So a little finger sticking out of my process that has the same temperature of the process. I put the thermocouple in there. The thermocouple measures the temperature, but it does so by the, for example, the relative expansion of two metals that each have different coefficients of thermal expansion. And by looking at the difference in thickness of those two, you know the temperature, because each one expands different amounts with respect to temperature. Then that's converted into a signal, an electrical signal, which is 4 to 20 milliamps, which then goes off to a display. And that display, typically, there are at least seconds between the temperature that's measured at the display. If that display is far away, it can even be a minute. There are seconds in there. Now, if I have some sort of feedback control, that means I'm going to look at this temperature, say the output. I'm going to have some sort of control algorithm that says that's good or that's bad. And if it's bad, I need corrective action. And then the corrective action is going to take place. So that corrective action is not going to be direct. It's going to be some sort of signal. And that signal has to be then converted into an action. So the signal has to be converted, the signal, which is typically milliamps, 4 to 20 milliamps, could be converted, could be a mile away from where the valve is. Typically, you want the control systems to be far away from your process, because if the process leaks or blows up, you don't want it to destroy your control system, your electronics. There's no reason it needs to be next to it. If you've ever, have you done any plant tours? With AICHE, have they taken you on any plant tours? That's a yes or no answer.
No.
No? You haven't been on a plant tour? When I was the AICHE advisor, we went on plant tours. You should tell your AICHE advisor you want to go on a plant tour and see what these things look like in real life. Okay, it's not hard to arrange. It's a couple of phone calls. In any case, then there's compressed air, which then can go in from anywhere, typically from 3 to 15 psi, which then operates a valve. A valve doesn't respond instantly, it takes seconds, a few seconds, and then that the flow has to, which is typically hundreds of meters away from the valve. Till the actual flow reaches the system, there's another delay. So notice, from the measurement until you go through the loop and the effect of the reaction to that measurement, seconds or minutes can pass, typically in a chemical system. Typically there can be minutes between the actual state of the system and the effect that the controller wants to do. Now, you can imagine if you have a very fast system or a very slow system. If you have a fast system, then the fact that it can take a couple of minutes to go through this loop means by the time the corrective action happens to your system, it's no longer in the state that corrective action was meant to correct. That can be a problem. And that's a big problem in electrical engineering. In electrical engineering systems, typically this time scales, those capital T's for electrical engineering systems, are fractions of a second. So the control systems have to be much faster and more sophisticated in electronic systems than they do in chemical systems. Luckily, most of the time in chemical engineering systems, the time scales, say, of chemical reactions that we deal with are typically hours, sometimes days, on occasion minutes. But typically, this couple of minutes of this loop here, that couple of minutes is usually negligible. And remember, what we want is we want the corrective action to reach the process based on the instantaneous state of that process. If by the time the corrective action happens, the process is somewhere else, not at the state I thought it was, then I'm going to have problems. And that's like the guy in the shower who turns the hot water, nothing happens, and then turns the hot water again. By the time the hot water comes out of the head of the shower, the water was already a lot hotter, and you get burned. So those delays, are something that in chemical engineering are usually less important, although sometimes they do come in. But in electrical engineering, they're there all the time. So we have, in a sense, usually an easier problem than the electrical engineers here in chemical engineering. Are there any questions on that? Okay, well, once I have identified control variables, disturbance variables, manipulated variables, I need to be careful here. That is, control variables are usually easy to identify. They're the specs. They're the specs on the product, and they're the specs on my system that says, you better not go above a certain pressure, otherwise you've made a bomb, not a chemical plant. You better not go above a temperature, otherwise you fry the electronics. So those are pretty easy, the control variables. They may not be that easy to control, but those are the variables we want to control. Now, manipulated variables are things I need to choose. When I say I mean you. The control engineer needs to choose. And the control engineer, for each control variable, has to choose at least one manipulated variable. And I mentioned this at the beginning of the semester. For each control variable, we want to have at least one, if not more, manipulated variable. So when I manipulate the manipulated variable, I change the control variable. So for each control variable, the control engineer chooses at least one manipulated variable that, one, has a strong effect on that control variable. Two, can change an effect without changing other things in the planet. So you don't want to turn a valve to fix one thing and it changes 20 other things. That's much too complicated. You also want the effect of the manipulated variable on the control variable to be fast. You don't want a half-hour delay until there's an effect. You want the effect to happen quickly. What else? You'd like it to be valve. Yeah. And hopefully, in the best case, the manipulated variable is changed by changing a valve. By changing a valve position. So those are the criteria that we usually look for when we choose the manipulated variable. As the control engineer, you choose the manipulated variables. Were there hands up or is everyone scratching? Okay. Maybe it's itchy in here. Maybe control makes it itchy to know the answer. Okay, so any questions on that? All right, well, in feedback control, we need metrics to measure how well we're doing. So we need metrics to see how we're doing. So for example, we can call the error is the difference between the set point and the actual value of the control variable. So we can call that the error. And obviously, we want to minimize, our goal is to minimize this. And let's make it the absolute value. So we want to minimize this. We also want to minimize, actually, so goals, what I call this, goals. And we also want to eliminate what's the word? A long-term difference, which is offset. We want to minimize or eliminate the offset. Where the offset is, at long times, the set point stays here, and the actual control variable can change, but it may have a long-term difference that never goes to zero. Even if that offset is small, that difference never goes to, if it never goes to zero, that difference is called the offset. And we want to eliminate offset. So you can sort of see the picture. This is the control variable. This is the set point. And I have the CV here. That's the offset. Even though the CV is, the error is small, it's not zero. And we want to eliminate that. What else would we like to do? We also want to make sure that things don't. So minimize the error, eliminate offset, have a rapid rise time. What's the rise time? The rise time is the time it takes to reach the set point for the first time. So, for example, here's the set point, and the system is disturbed. So it's going along nicely, the system's going along nicely, and then there's a disturbance. And now the rise time is this time here it takes to actually reach the set point for the first time. Typically, if I make that time too short, then I'm going to overshoot. But one thing at a time. The rise time, what we don't want is it to take forever to get to the set point. This is a very long rise time. Here's a short rise time. So, on the one hand, we want to have a rapid rise time. On the other hand, we want to minimize oscillations. So if I go too far, I can way overshoot and go up and down and up and down. There's also a decay rate. If I have oscillations, I want a fast decay rate. So what is a decay rate? So this is time. Here's the set point. And so if I overshoot, then I keep overshooting, and hopefully it continues to shrink. So the decay rate is the ratio between adjacent peaks. So if this is A and this is B, the decay rate is A over B. So if it's going to oscillate, I would like A over B to be small. I don't want this to be close to 1. I certainly don't want it bigger than 1. But I want A over B to be small.
Is there ever a time when your set point is a range of values are
Sure.
So in that case, will the offset just be the operator will
Yeah. It all depends on what the specs are. Obviously, if you want 95% purity is your spec, if you get 98%, no one's going to complain. So it's not just 95. You don't mind going above it, you just don't want to go below it. But certainly, it all depends on the details of your process and your customer. Okay, so how about some metrics? What metrics could we use to measure the error? Well, one of them would be the integrated error on E. So that's the integral from 0 to t of the error E of t dt. Where, and typically this t might go to infinity. Where remember, the error is the difference between the set point and the actual value. Now, and let's not even put the absolute value in here, it's the integral of the error. The integral of the error, the problem with that is if the error oscillates, then the negative regions will cancel the positive regions. So this won't give you a good, this won't give you necessarily a good representation of the error, because negative errors and positive errors will cancel, and that's usually not what you want. So instead, we often use the integrated absolute error. And that's the integral, the magnitude of E of t prime, dt prime. And I think we usually let these go to infinity, the upper limits, right? Well, I'm not, it could be a function of time, so I'll leave it as is. This at least doesn't have the negative parts canceling the positive parts because I'm taking the absolute value. Sometimes I don't like absolute values because absolute values are not differentiable at 0. So in order to avoid that, I could look at the integral square error. So instead of taking the absolute value, I square it, and that again turns the negatives into positives, so they don't cancel. And finally, if I have, so notice if I have a non-zero offset. If I have a non-zero offset, well, the integral of the error with respect to time is going to grow, but if the offset is small, it's going to grow very slowly with time, because this is a small number. If I really want to, I really place a strong emphasis on not having an offset, then what I might want is to have a penalty go up with time. In other words, what I could look at is IT AE. Or should I do it with the square? Which one do I? ITA. Yeah. So this, the ITA, is the integral from 0 to t of E of t prime magnitude, just like here, but then I multiply by t prime dt. t prime. So this says that if I have this offset that persists for a long time, since I'm multiplying by t, I'm multiplying this difference by t, the longer it lasts, the bigger the penalty, the bigger the error, the bigger this calculated error is. So this penalizes persistent offset. When I say penalize, what I mean, it says bad, bad, bad. When you have an offset, and that information goes to your controller, to your feedback controller, or your control algorithm, and it's seeing a huge integrated time absolute error, and it says, I really need a strong corrective action. If I only had the integral absolute error, well, it would be getting bigger, but not very quickly. So the controller might not react that quickly. Whereas if I'm using ITAE, this will cause the controller to take action much more quickly if I have what looks like a persistent offset. Any questions on those things? Okay, so a couple of other words here. One other terminology is the settling time. It's the time needed, time until control variable gets to and stays within 5% of set point. So typically that's called the settling time, and hopefully you want that to be small. So even if you have an offset or if you have a small oscillation, as long as that's within 5% of your set point, then that's considered that your settling time is till you get there. Sometimes that's good enough, sometimes it's not. It all depends on how tight your specs are. Finally, when it comes to goals, so let's call this a goal. We want to minimize the settling time. This was 6. And 7, naturally, we want the control variable to go close to the set point. But we also have to remember, mechanical things break if we use them too much. So we also want to make sure that my manipulated variables are not manipulated too much, not doing too much on and off. So if I'm turning a valve open, close, open, close, open, close, open, close, eventually that valve's going to break. So I want to sort of try to minimize that, and I can look at the value of the manipulated variable as a function of t minus the value of the manipulated variable at infinity, or the value of the manipulated variable at infinity. I can look at that, and hopefully I want to make sure that this thing doesn't get too big if I integrate this. The basic idea is you don't want to constantly be turning the valves on and off, because eventually they're going to break. So you not only look at, so for example, you not only look at the oscillation of the control variable, you also look at the manipulator variable, is it oscillating? And that's one of the reasons we're not crazy about oscillations. So for example, so let's say here's the set point, and here's the manipulated variable. If the control variable looks like this, but to get there, the manipulated variable has to do this. This is not great for the manipulated variable because you're constantly turning it on and off. So this is something you kind of want to avoid. What you would prefer is if the control variable, so here's the control variable goes up. Maybe the manipulated variable will go way down. And then gradually go back. And hopefully that will cause the control variable to gradually go back. This is a much better performance for the manipulated variable than constantly shifting it on and off, even though they go back to the set point in roughly the same amount of time. Now, let's go back to what we remember from the early part of the semester with statistics. When we want to look at the control variable, the statistics of the control variable, we have a mean value of the control variable, which is, say, if I have n measurements, 1 over n times the sum of the control variables of j measurements. And I also have a sigma of the control variable, which is the square root of CVJ minus CV bar squared over n minus 1. Sum. So I have both the mean and the standard deviation of the control variable, which are statistical measures of what the control variable, of the value of the control variable. And again, the kinds of disturbances we've been looking at in this class are either step disturbances, pulse disturbances, or oscillatory disturbances. Now, I want you to notice that some of these criteria are in contradiction to each other. If I want a rapid rise time, well, if I have too rapid a rise time, then I'll overshoot, and then I may get oscillations. If I want to minimize the oscillations, I may have to take a very gradual control, and then it'll take me forever to, the rise time will be very slow, and the settling time will be very slow. So a lot of times these, as long as I'm not in a completely first order system, a lot of times these trying to fulfill one criteria makes the other criterion worse. So typical control is a compromise between your goals. So we make a compromise. Something that is always good in life to be able to make compromises. We certainly have to do it in control. And what types of control are there? So types of control. So 1, no control. Praying. So no control. One example of no control is gun legislation in the United States. We hardly have any. So we just hope that people don't just buy guns and kill each other, because there's no control. Yes?
The second one, is that the same as the standard deviation?
This is the standard deviation.
Are they both the same? Not the one.
You know, with the mask, I can't understand what
Are
you're saying.
they just the sample and not the whole deviation?
We have a control variable. We're measuring the control variable at multiple time points. The data we have are the values of the control variable at multiple time points. So we calculate the average, and we calculate the standard deviation. So, and n is the number of measurements that we make. So I'm not sure I understand the question.
I'll ask you.
Okay. Okay, so the first type of control is no control. Don't do anything and hope that you get the product you want. The second type of control is manual control. So that's sort of like when you're in your house and it's too hot, then you turn the radiator down. Or in New York, where the radiators don't do anything, if it's too hot, you open the window and waste energy. If it's too cold, you close the window. That's manual control. Now, you can do that in your apartment if it's too hot. or too cold, because you have no choice. And that kind of works, but you have one variable you're worried about. In a plant, you may have 1,000 variables you're worried about. So you can't expect one person in the control room or two people to do manual control on 1,000 different variables. So another type of control is bang-bang control, sometimes called on-off control. Now, if your apartment is not that old, see many of the apartments in New York, the boiler is on in the winter and off in the summer. So the boiler is producing heat all the time. And whether it's hot outside or cold outside, whether it's 20 degrees above or 20 degrees below, and you vary, and the valves on your radiators don't work very well, so you control the temperature by opening the window or closing the window. In the newer apartments, there are thermostats that when the temperature goes above a certain value, it actually shuts the boiler. Or if you like, it shuts some valve that taking the heat to your apartment, because maybe other apartments are colder. So, but all it can do is on or off. Either the boiler's on or off. Either the valve is open or it's closed. So that's, and that works pretty well for simple systems. There's also continuous automatic control. Now that's if it's a little more sophisticated. When it's too hot, instead of shutting the valve all the way, it can shut it part way. And that way, it can try to find a value of the valve that's maybe neither fully open or fully closed that gives you a steady state, so it's not constantly going on and off. So that's continuous automatic control. And then, and pretty much in the realm of what we're trying to do here, we're going to try to work with continuous automatic control for once we have a good control algorithm. But finally, we also have emergency control. If you remember, in the diagram I drew, probably in the second or third class, we had the situation of a plant, or at least part, we had a distillation column, and where we had, at the top of the plant, where we had the gas stream, the vapor stream coming out, going to a condenser. We were measuring the pressure on the condenser. And if the pressure on the condenser was getting too high, we opened the valve and we allowed the liquid to go, we increased the flow rate of coolant into the condenser so that more of the vapor would condense and then go back from the condenser back into the distillation column. But if that failed, we had an emergency control system, which then would essentially just open up the condenser and dump everything into containment in order to make sure that the system didn't blow up. So that was called emergency control, and the point there was we used a controller for the emergency control and also a valve that was much more heavy duty, much more reliable, but that's rarely used. It's rarely used, but it's very reliable. You want to make sure that when there's a danger of hurting people, destroying the equipment, hurting the environment, actually hurting people, hurting the environment, hurting equipment, then you have emergency control that will mitigate that will make sure that doesn't happen. So those are the 5 types of control that we're going to be talking about here. Are there any questions? Yeah?
I guess I'm curious about an example of not the bang-bang, the continuous automated control.
That's what we're going to do for the rest of the semester, so you'll have lots of them. In fact, I'm going to do 2 examples right now.
So for the continuous, it's normally like processes, like professional processes. Not
Typically, yeah, this is typically, for what we're going to be using, we're going to be doing continuous automatic control. So even at the end of the hour, if you should, by the end of today's hour, you should see some examples of that. Other questions?
I was looking at that, or thinking about that integrated error. It's going to continue to grow.
If there's an offset. The idea is, if there's an offset, it'll continue to grow, but if the error grows, then the controller is going to be alerted saying that error is getting bigger and bigger. We need to do something. So the controller will increase its action So we'll increase the continuous action. We'll continue to open the valve, if that's what is the corrective action. Continue to open it until it stops growing.
But that interval is adding that error. I know, maybe we'll get there.
Until the integrand goes to 0. When the integrand goes to 0, then it stops growing.
Will it ever go to 0?
If you design your control system correctly, that's exactly what we're going to be doing.
Okay.
No, these are the right questions to ask, because this is motivating what we're going to be doing for the next couple of weeks. Was there another hand up? Okay, so for control, we're going to have 2 canonical examples. When I say canonical examples, what I mean is there are going to be 2 examples that we're going to refer to whenever we talk about different control schemes. So what I'm going to do for the rest of the hour is go through 2 examples. The canonical example 1 and canonical example 2. And if hopefully you've looked at Blackboard. At the end of the last hour, I mentioned that earlier in the semester we had done it, but I mentioned that I would post in Blackboard an example where you actually have 2 things that are changing, 2 disturbances, and looking at the output. Because most of the time we had done examples where we had 1 disturbance and we looked at the output. But as we mentioned earlier in the semester, when the system is linear, or when we've linearized it, the linearized system, even if you have multiple disturbances, they just add. It's very simple, and I did an example of that. Now, what's important about about control is that's actually the natural state of control. Because typically, you'll have a disturbance that's affecting your system, and then the controller will change something else, will manipulate a variable. So if you like, you'll have 2 things that are changing. The disturbance is an input, and the manipulated variable is an input, and you want to look at the output, what happens to CV. So you have a disturbance that's changing that you don't control. You have a manipulated variable that you do control, but they're both changing, and you look at the effect on the control variables. So let's look at the following example. So here I have theta in, and here I have theta, and I have theta coming out. And I also have a cooling system here, and let's put the valve in lower. And I measure the concentration here, and I adjust the valve. So here I have VC. So let's just notice what happens here. And, yeah. So I have a stream coming in at a certain temperature. I have something going on in the reactor that affects that temperature. So I might have a reaction going on there. It affects that temperature. The temperature, and since it's CSTR, the temperature in the reactor is the temperature that comes out. If I don't like that temperature, and of course I also have a concentration that's coming out, but presumably, and actually let's just call this A theta. So this means I'm measuring theta. I'm measuring the temperature. If I don't like that temperature, then I change the volumetric flow rate of the coolant stream by changing the valve opening. And that will cool this down if I open it, or if it will cool down less if I close it. So, and let's assume, so let's say my control variable is theta. My disturbance, I may have a disturbance in theta in, and my manipulated variable is VC. Is that clear? Let's just make sure the disturbance variable is correct. Disturbance for that, right. And I'm going to notice that there's a UA that is the overall heat transfer the overall heat transfer coefficient of the heat exchanger between the coolant stream and the reactor fluid, this is a function of VC. I'm not even going to specify it, it's just some function of VC. We spoke about that earlier in the semester. It typically goes as VC to a power where the power is less than 1. It depends on how turbulent the flow is. Okay, so let's write out d theta dt. D theta dt times is equal to theta in minus theta over tau. Why tau? Because here I have, actually, why don't I just write the whole thing? So here I have rho v CV is equal to rho little v CP. And again, I'm going to assume that CP is CV. Times theta in minus theta. Plus UA times theta minus theta C. See on the above or below? No, it doesn't matter. Theta C. So how does theta change? How does the temperature change? It changes. I've got fluid coming in at a certain temperature. I've got fluid going out at a certain temperature. And then I have heat transfer between the coolant stream and theta. And I think I have the sign backwards. This should be plus if the coolant stream is hotter than the outward flow stream. So now I divide through by rho v CV. And what do I get? So I have theta dt is equal to, well, here, capital theta. So here all I have left is little v over big V, because Cp and Cv are the same. So this is 1 over t, tau. Theta in minus theta. And here I have UA over rho v Cp, because Cv is Cp, times theta C, and this is a function of Vc, minus theta. And now what I want to do is use some color chalk to look at what's changing. Okay, so there's a disturbance to theta in. So theta in is certainly changing. I'm going to manipulate Vc. If I manipulate Vc, UA changes. Because it depends on Vc. What is going to change as a result of that? If I were, by changing theta in and Vc, what else is going to change here? I can't hear you. The temperature of the outlet, theta. So let's use a different color for that, because that's the effect. So theta is going to change. So now let's notice our terms linear and nonlinear. Linear means I only have one non-white color, and nonlinear means I have two in the same term. Linear or nonlinear? Linear or nonlinear? Linear or nonlinear? Linear or nonlinear? Linear or nonlinear?
Non-linear.
Nonlinear. So I have to linearize that. So in order to linearize that, I have UA over rho v Cp theta. Let's linearize that. Well, and in fact, I can actually do the whole thing. It doesn't hurt to do it this way. So this, and again, let me emphasize what's changing, right, with colors. So I'm going to assume that for t less than 0, system at steady state. So this is equal to UA rho v Cp steady state, theta C minus theta steady state. let me just remind you what we're looking at. We have f of xy is equal to f of x0, y0 plus the f dx at x0, y0 times x prime, well, x minus x0, which is x prime, plus the f dy at x0, y0 times y minus y0, which is y prime, plus nonlinear terms. So I'm not going to worry about the nonlinear, so I'm going to say approximately. So this is, so x in this case is vc, and y is theta. So I need to take the derivative of this thing at vc. So I have dua dvc at steady state times 1 over rho vcp, those are just constants, they come along for the ride, times theta c minus theta prime. Now, of course, theta c prime doesn't exist. There is no theta c prime because theta c minus what it started with is just itself. I need space for the other term, so I didn't leave myself, so I'm going to bring it up here. Plus the derivative of this thing with respect to theta. With respect to theta, this just drops out. So then I just have, so I have the derivative of this with respect to theta. The derivative of this with respect to theta is u a over rho. Actually, did I do that right? No, I didn't do that right. Sorry, let's start again. One thing at a time. I'm taking the derivative with respect to VC. So the derivative of the whole thing with respect to VC is the derivative of this with respect to VC times theta C minus theta steady state times VC prime. Because x prime is VC. I took the derivative with respect to VC, I need a VC prime. Now I need to take the derivative with respect to theta. The derivative with respect to theta is everything else. So I've got UA over rho VCP steady state times theta prime with a minus sign times theta prime. The minus sign is because there was a minus here. And then I have plus nonlinear terms. So now what I do is, so this is the exact. So now let's take the linearized for t greater than 0. So that's d theta dt is equal to theta in minus theta over tau plus u a rho vcp steady state theta c minus theta steady state, the one at steady state, plus this guy, which I'm just going to call alpha so I don't have to keep repeating it. Alpha VC prime minus UA over rho VCP steady state theta prime. So all I did is I copied these three terms for this one term. Now I look at the exact for t equal to 0. That's the theta steady state dt is equal to theta in steady state minus theta. And yes, over tau steady state plus UA steady state over rho v CP theta c minus theta steady state. Plus alpha plus nothing. This is just at steady state. So I take the exact and I evaluate it at steady state. Now I subtract. When I subtract, I have d theta prime dt is equal to theta in prime minus theta prime over tau, where again prime is the value minus the steady state value. Value minus steady state. Value minus steady state. Plus, these two terms are exactly the same, so they cancel. So now I have alpha VC prime minus UA steady state rho VCP theta prime. Is that clear? Now what I'm going to do is what we've been doing all semester. All the theta primes to the other side of the equation. So d theta prime dt plus theta prime times 1 over tau plus u a at steady state rho v cp is equal to theta in prime over tau plus alpha vc prime. And before I go on, I want to look at this for 1 second. Notice the left side of the equation again is the system, the right side of the forcing. This is the disturbance, this is the control action. Disturbance, and this is the manipulating variable due to control. And notice, because we linearize the system, the effects of the disturbance and the effects of the control add. They add. Okay, well, let's do what we usually do. We're going to call this thing 1 over a time constant t, and we're going to Laplace transform. When we Laplace transform, we have s times s plus 1 over t, which is 1 plus st over t, times theta prime tilde is equal to 1 over tau theta in prime tilde plus alpha vc prime tilde. Or I have theta prime tilde is equal to theta in prime tilde times t over tau 1 plus st plus vc prime tilde times alpha t over 1 plus s. And I want you to notice that this thing is the G for the disturbance. And this thing is the G tilde for the control. Or for the manipulated variable. So what's the take-home message here? The important thing here is I haven't even specified what the control is. How VC is going to change. I will do that. But I want you to notice that I have a G, a transfer function, for the effect of the disturbance on the control variable, and another G for the effect of the manipulated variable on theta. And that difference, and those two add because we've linearized. Are there any questions on that? And we're going to go back to this to figure out what VC prime is. VC prime may have a time, VC prime may have a time dependence. So I'm not going to invert this yet because there might be more S powers in here, functions of S here. Are there any questions on that? Okay, so in the last 15 minutes, let's do the next canonical example. So here's a situation where I have 3 CSDRs in series. And I analyze what comes out here. And what comes in here is I have, so I have an X and an X, and this is A, and this is XB. And I've got a volumetric flow rate B and a volumetric flow rate A. So what happens is I have an inlet stream with a mole fraction of species A in the inlet stream with a volumetric flow rate B. It goes through 3 CSDRs. each with a reaction A goes to B. And if I don't like what comes out, what I can do is I can spike the feed. So I want a situation where XAB is much bigger than XAA. So if I don't like the output, I can just add in a little bit of this stream, and that increases the concentration going in here, so that will affect what comes out. And I also want a situation where typically VB is much, much bigger than VA. So most of the flow is this stream, but I can always spike it with a little bit of stream A. Is that clear? Yes? No? Clear? Okay. So, and I'm going to make life easy. I'm going to assume V1 is equal to V2 is equal to V3. Meaning tau 1 is equal to tau 2 is equal to tau 3, because I'm going to assume that the reaction is constant density. And so what's going to happen here? I need a control variable. The control variable is XA3. I'm going to have a disturbance, and I'm going to have a manipulator variable. My manipulator variable is VA. And my disturbance is going to be, I believe, to XA to the X. Disturbance is XAB, yes. So I have disturbance to the input concentration, or mole fraction, and I manipulate VA. Clear? So for each reactor, D XAI, so this is XA1, XA2, XA3, and let's call this XA0, which is equal to XA. So I have dXAI dt. And when I'm dealing with X's instead of concentrations, because the concentration, recall, is CA reference times 1 minus X. So the X's have a negative sign relative to the concentrations. So I have XA I minus 1 minus XAI. Actually, I can just derive it from it. So we have the CAI dt is equal to CAI minus 1 minus CAI over tau minus K CAI. I do want a first order reaction, right? Yes. Okay, so now if I let CA to CA ref 1 minus X, I have a minus, I've got CA ref reference times minus dXAI dt is equal to CA ref over tau times 1 minus XAI, so minus 1, minus 1 plus XAI minus K CA ref 1 minus XAI. And this is true for I equals 1 and 4. So you can see that the CA refs cancel, and the minus sign makes the XAI dt, that's T, is equal to the 1's cancel. And the minus sign flips the signs here, so I have XAI minus 1 minus XAI over tau. Minus a minus and a minus is my minus KXA. So that's just going from concentrations at constant density to mole fractions. And now again, the XAI dt plus XAI over tau, move these guys to the other side of the equation, plus K is equal to XAI minus 1 over tau That's it, xi minus 1 over tau. So, yes?
In the second line, you have it as 1 minus XAR, where did the 1 go?
Where did the 1 go? Let's see. Good question. Did I drop the 1? Let's see. I'm sorry?
Wrong mistake.
I don't see it right now. I'll fix that next time. I just would like to go on here, but remind me that and I'll fix it next time. Okay, so the question is what output is 1. We'll figure that out in a little while. Let's just note that this is 1 over t. And when I Laplace transform, I have 1 plus s plus 1 over t, which is 1 plus st over t. xai well, okay. This is the unstable. Now, so this is and this is linear. Because the only thing that's changing are what's going into the XARs. The taus and the k's are not changing. So the steady state value at t equals 0 is dxai steady dt plus xai steady over t is equal to xai minus 1 steady over tau. When I subtract, I get dxai prime dt plus xai prime over t steady state. Is equal to xai minus 1 prime over tau. And now when I take the Laplace transform, I have 1 plus st over t. xai prime tilde is equal to xai minus 1 prime tilde over tau. Or xai prime tilde is xai minus 1 prime tilde times t over tau 1 plus st. And let's now count. Now we're interested in xa3 in terms of xa. So I've got now xa3 in terms of xa2, xa2 in terms of xa1, xa1 in terms of xan. So let's rewrite that as xa3 prime tilde. Well, to get to xa2, I have a factor of this. To get to xa1, I have a factor of this. To get to xan, I have a factor of this. So this is equal to t over tau cubed, 1 plus st cubed, times xai in. xa in. Right. Where xan is xa0. And now I need to write out what xan is. What is xan before I do the prime and I do the tilde? Xan is a mixture of this stream and this stream. So it's equal to VA XA plus VB XB. So this is the amount coming in, the amount of A coming in. This is the volume per unit time in the A stream times the mole fraction of that, that's A. That's the amount of the moles of A coming in the first stream, the moles of A coming in the second stream. And I want a mole fraction, so I need to divide by the total number of moles that are coming in, which is over VA plus VB. And now we need to notice what's changing and what's not changing. Well, we said that XAB can change. XAB is the disturbance. XAB, it changes. And the manipulated variable is VA. That also changes. VA also changes. And notice, this is nonlinear because I've got a VA in the denominator. I've got a ratio. So I have to linearize. So let's look at what XA is. And again, I'm appealing to this. So in this case, if I do in terms of x and y, x is XAB, and y is VA. So this is equal to VA XAA plus VB XAB over VA plus VB steady state. That's this guy. And now I need to take the derivative with respect to XAB. So I'm going to have an XAB prime times the derivative with respect to XAB. Something that people maybe were having some trouble with last time is if I take the, well, this one partial derivative is easy. There's no XABs in the denominator. There are none here, so I just get a VB over VA plus VB. Because the first term has no XABs in it, so the derivative of that is 0, and the derivative of that with respect to XAB is just VB over VA plus VB. And then I have another thing, so here I have a VB prime. And why don't I do it below so the rope doesn't get in the way? So now I have VB prime, VA prime, VA prime times something. Now, unfortunately, 2/3 of the class didn't know how to take the derivative of a quotient. This is freshman calculus material. So there's VA in both the numerator and the denominator. So I need to take, if this is F and this is G, the derivative is F prime G minus FG prime over G squared. So first let's put in the G squared. VA plus VB squared. F prime. So I need to take the derivative of the numerator with respect to VA. Well, the only place I see a VA is here, so I just get an XAA. And that's multiplied by the denominator, VA plus VB. F prime G. And now minus FG prime. So let's copy the numerator. VA XAA plus VB XAB. F times G prime, the derivative of the denominator with respect to VA is 1. So now I notice that I have a VA XAA here, subtracting a VA XAA there. So what's left is equal to VA XAA plus VB XAB over VA plus VB plus XAB prime times VB over VA plus VB plus VA prime times something. Well, the denominator is VA plus VB squared. And the numerator has the XAA VB minus the VB XAB. VB XAA minus XAB. And then I still have plus nonlinear terms, which I don't care. And I think the last thing I'm going to be able to do here today, we'll continue next time, is I want to apply these criteria. These two. So let's notice that this term, I'm not going to rewrite, it's there. if VB is much, much bigger than VA, I can ignore VA with respect to VB. Because VB is much, much bigger than VA. If I ignore that, then the VB's cancel, and I just get an XAB prime. Now, over here, XAA is much, much bigger than XAB. I'm assuming XAB is much much bigger than XAA. And did I have this right? Yeah. XAB is much, much bigger than XAA. So I can ignore the XAA. And I can ignore V, which is bigger. VB is much, much bigger than VA. So I ignore that. So I have VB over VB squared is 1 over VB minus XAB. So I've got a minus XAB over VB. Minus XAB, because XAB, do I have it right? No, XAA is much bigger than XAB. I think I did backwards. This is backwards. A is bigger than XAA is bigger than XAB. This is high concentration. Yeah, this is high concentration, this is low concentration. So let's go back and fix that. XAA is much bigger than XAB, so this is negligible. So it's XAA. VB is much bigger than VA, so this is negligible. VB over VB squared is 1 over VB. So I just rewrite this, VA XAA plus VB XAB, steady state. VA plus VB, steady state. And this is XAA. This is the steady state value, and the last two terms, if I subtract off this, which is the steady state value, the last two terms, which I have no place to put them, these two terms are XA in prime. Because it's XA in minus the steady state values. XA in prime are these two terms, which the last equation I can write, if I have a place to write it, is here. So it's XA 3 prime up. So XA in prime tilde is equal to XAB prime tilde plus VA prime tilde times XAB divided by VB. So all I did was I tilted this and I tilted that. And what I should do is actually have this last equation, which is the one I need. XA3 prime tilde is equal to, it's equal to T over tau cubed, 1 plus ST cubed, times XA in prime tilde, which is XAB prime tilde, plus T over tau cubed over 1 plus ST cubed, times XAB over VB times VA prime tilde. And this is the final equation for today. And what can we see about this equation? What we see here is exactly what we saw here. I have XA3 prime tilde is equal to a G for the disturbance times XAB and another G for the manipulated variable for VA. So again, in both of these cases, we had, in both of these canonical problems, we had a control variable here and here, theta is the control variable. We had a disturbance theta in, disturbance XAB, and we had a manipulated variable VA and VC. And what we solved for was the control variable prime tilde, theta prime tilde, theta prime tilde. Here, control variable prime tilde, XA3 prime tilde. And that was equal to a G for the disturbance times the disturbance prime tilde. The G for the disturbance times the disturbance prime tilde. Plus a G for the manipulated variable times the manipulated variable prime tilde. And that, again, they add because the system has been linearized. Okay, I went a little over, sorry about that. Are there any questions? So next time, we're going to start talking about how to put this all together and how to do control. We'll also have one class where we go through, at least for part of the class, how to use Simulink, this program. Now, a little background. This already is chapter 7, I believe. We have, next week is the ChE meeting, so I will be gone at least Monday. I haven't bought my ticket yet, but I may be gone on Wednesday as well. So what we imagine we'll have an exam a week from Monday. Not this coming Monday, but the following week. That's the current plan. Make sure you have your homeworks in, all those homeworks on everything through before the start of control, everything through the end of the last class. This already is the material after the second exam. We'll try to get your homeworks back to you before the exam. I'll also post on, since the person who was responsible for these videos hasn't put them up yet, maybe you'll be able to, but send me the link from the ones from last year, the videos from last year, which basically is the same material. Are there any questions?